So now that we've seen some of the basics of how you could fit a GAM mathematically, let's turn to R to see how we would implement this in practice. And we'll do this through the Unit 7 code. We'll look at problem number 3, where I simulate some data, and then we analyze it with a few different models. And then you will have some practice implementing a GAM in problem number 4, which uses some real data. So in this simulation, I want to construct some data that has a Poisson response and a few different predictors. And so this will be a generalized additive model in the sense that it is generalized from just a normal response. We'll use a Poisson response. So the predictors that I'll use here will have a few different ones. So x1 will be a continuous predictor. x2 will be a categorical variable, and x3 will be a logical. And importantly, x1, the continuous predictor, will have a nonlinear relationship to the response. And that's really what we're trying to capture here, is that a GAM can pick up on that nonlinear relationship pretty well. All right, so this code cell will simulate the data, and we're going to simulate 100 data points. And first, I just want to construct those predictors. So here, we're constructing just a continuous predictor x1, and soon we'll relate that to the response. Here, we are constructing a factor as our x2, and I'm just sampling from, say Sunday, Monday, Tuesday. And then here, we just have true and false values that we're sampling from. And down below, you see what those predictors look like here, right? Continuous predictor samples from those letters and true values and false values. So that's simulating the predictors. Now we want to relate those predictors to the response. So this is all in me sort of simulating data, which means making up the data. That way I know the relationship between the predictors and the response. And then when we use the modeling, we have a sense of what is right and therefore how well our model can perform. So of course this is different than the context you would be in if you were actually using this model on real data, because you wouldn't know the answer. But when you're studying these things, it's nice to know the answer so you can see how well things do. All right, so to construct a Poisson response, what we'll do is take a linear predictor. So here's the form of the linear predictor that I'll use. And notice, really the important thing for GAMs is that I'm saying that x1 has a nonlinear relationship to a function of the mean response. And so what I'll do is I will construct mu based on that linear predictor. So in this code cell down here, I'm constructing mu by exponentiating this term here, right? Exponentiating this here. And so I've got the log of 1/2 x1 squared, and then I'm subtracting off x2 and adding x3. And notice that here we're making beta 1 equal to 0. So the true model has beta 1 equal to 0. Now this is a vector. It's of length n, and it represents the mean values of a response that I still need to construct. Well, if I want my response to be Poisson, then constructing the Poisson response should be pretty easy. It says, all right, my response will be a randomly generated Poisson. I want n of them, and I'm going to feed it in a vector of length n. So that means every entry in this vector will have a different mean according to how this mu changes. And so you see that here in this data frame. So notice the y's are just counts. That's good because it should be Poisson. And the mean is different depending on the values of your predictors, right? So that's done on purpose. That's by construction. So we could look at some summaries. Of course, we can look at a plot of x1 as a function of y. And we notice like there are different groups here. Those groups are going to correspond to our factor variables. And our goal is to try to make predictions. Suppose you're in the M group and your value is true on the other variable, and you're at, I don't know, 45 on x1, what could we predict as your response? And we'll see that GLMs, so just generalized linear models, won't do as well as a generalized additive model because of the nonlinear relationship between x1 and the response. So that's really the goal, is for us to see that. All right, so let's start with fitting a generalized linear model. You should be experts at this using the GLM function. So here we're just fitting as if the terms entered linearly. Right? We're supposing we don't know the true relationship. That's what modeling is all about. So we say, okay, well, I think there's a linear predictor. It involves the 3 predictor variables. We've got our response variable coming from the data frame D. And, well, I know that the response is a count, so I will use Poisson regression. All right, so let's look at some ways to assess this model. Of course, we can look at residuals versus fitted values, which we see here. And this doesn't look too terrible, but we do notice that there's some structure, right? There are these structured groups here, and maybe we can think that there's some sort of wavy pattern. It's not terrible, but it doesn't look ideal. And if we look at normality, so the normality of the residuals, we see deviations from normality down here, which suggests that maybe this model doesn't fit super well. And then we can look at fitted values versus actual values. And so what we should see here, right? I'll show the code up here. We're plotting the fitted values from the generalized linear model against the actual values. And we really want to see that they line up along the line y is equal to x, right? You want your predictions along the x-axis to be very close to the true values. Well, they do actually really well down low, but then as you move higher in the predicted values, things get a bit worse, right? Things get worse. And this is due to the nonlinear structure that we have for x1. At least that's the hypothesis right now. Let's see if we can do better with our other models. We can also assess the fit of the model and sort of compare models using the MSE. So here we'll just note that the MSE for our generalized linear model is about 7.9. And we'll keep that number in mind and compare it to the 2 other models that we fit, one of which will be a GAM. All right, so now let's do a quick run through of what it would look like if we used a generalized linear model, but we use the exact relationship that we constructed the data with. So of course, in any real context, you won't be able to do this, but this is sort of our baseline. Like, this should probably work best. And our GAM is, our GAM later on will do its best to try to learn this relationship here. All right, well, if we look at residuals versus fitted values, this looks a bit better. There's less structure to be seen. It really does look like random scatter around 0. Maybe there's some, some outliers down here, but really not too bad. So that looks decent. Normality looks, well, a little bit better, not great. There's still some problems down here and maybe a few problems up here, but I think it does a bit better than above. And in our actual values versus the predicted values, we seem to do a lot better, right? We have more values lining up across this line. So that means our MSE should be lower, right? We have less deviation up here, less deviation through the middle. So we should have a lower MSE. And that's exactly what we see, right? This MSE, if you compare it to above, which was just under 8, we've done a lot better in fitting. And that's to be expected because we've used the true relationship. Well, that's cheating, right? It's cheating to use the true relationship. Why don't we think about what would happen if we tried to learn the true relationship? Well, here's the way to do it in R. using the MGCV package, which has a GAM function. And this GAM function is just like LM and like GLM. We need to specify a relationship. So relationship between the response and predictors, a data frame, what family it is. So this allows for you to use, say, a Poisson family, as in this example. But you could also use a normal family, a binomial family, etc. But where GAM really shines is that it allows you to try to learn nonlinear relationships. So by wrapping x1, remember x1 is our continuous predictor that is has a nonlinear relationship to the response. By wrapping it in this S function, that tells the GAM function that it should learn the spline relationship, right? It should learn some sort of cubic spline. And so notice that this GAM function will use the penalized smoothing splines method for fitting the GAM. So that was the previous video. There's another library called GAM, and in that library there's a GAM function that you can use to fit, and this library will use the backfitting algorithm. So that's why I mentioned the two different algorithms for fitting, because there are two different R packages that use two different methods for fitting GAMs. But let's stick with MGCV. And we'll take a look at the same metrics. So we'll have residuals against fitted values. Here, this looks pretty close to fitting the true model, and the residuals look pretty good. Looks like, normal noise around 0, so that's nice. QQ plot, again, not great, but not terrible either, so some deviations in each one of the tails, but typically our assumptions are fairly robust to normality, so that's not a huge problem. And the nice thing here is that we've learned the relationship. We didn't just assume the true relationship. And we're noticing that as we move across in our predicted values, the responses seem to line up right along the line y is equal to x. So we're doing really well in predicting all the way throughout, as opposed to the GLM, which stopped predicting well for higher values. So that's really great. That's where we see the generalized additive model really shining. And we notice down here the MSE for the GAM is low. It's actually lower than knowing the true value. And I think that's just an artifact of the simulation that I actually did, because as we look below, we'll do some predictions, some out of training set predictions, and we'll notice that the MSE of the GAM is a little bit higher than knowing the true value. But they're roughly the same, and that means that the GAM is doing pretty well, almost about as well as knowing the true relationship, and certainly much better than a generalized linear model. All right, so let's think about some other ways to assess GAMs. Well, we can do a summary, just like we do for other models, and we see a lot in the summary. And there are a few things that I want to point us to. So notice the table here for GAMs tells us specifically that these are for parametric coefficients. And notice that the continuous predictor x1 does not show up in this table. And that's because we fit x1 non-parametrically, right? So we have a splined fit, and that information shows up here. And so we'll analyze this information in just a second, but let's go to the parametric fits to see some really nice feature about a generalized additive model. The nice thing is that these estimates, which you get from penalized least squares, or you can also interpret it as a penalized maximum likelihood, these values can be interpreted in a very similar way to values in a GLM, so the Poisson GLM. For example, the intercept term you can interpret as being at the M level of x2 and the false level of x3, right? So those are sort of like control groups if we use the language of experimental design. So that tells you the mean value of the response at the control values of the predictors, holding this constant, right? Holding x1 constant. And then, of course, if you want to interpret, say, a 1-unit change in x3, that would be going from false to true. So what would it look like to go from the false group to the true group? Well, you would have about a 1-unit change on average to the response. And so you could do similar interpretations here. And importantly, that's holding x1 constant, right? You're controlling for x1, but you're doing it in a nonlinear way. So that's really great. You still have an interpretation of the parametric coefficients. So those are the coefficients associated with terms that enter the model linearly, adjusting for the nonlinear terms. So that's a real virtue of GAMs, is that they allow you to still interpret them for the parametric terms, adjusting in the right way for other predictors. All right, so if we want to interpret the fit of x1, so what is this spline fit? There are a few different things for us to look at. We will mainly look at visualizations. So let's go down to a visualization of the fit of, the spline fit against our x1. And notice that there's certainly some curvature here. And, the interpretation would go something like this. So this this line, the line in between the two dotted lines, is really the predicted dependent variable as a function of x1. And we should say, adjusting for the other predictors. And if we're interested in learning whether we should do a linear fit as opposed to this curved fit, we could ask the question, is it possible to draw a straight line between these confidence bands? So the dotted lines are our confidence bands. And it seems like in this case we can't do that, right? A straight line would go well outside of the confidence bands. So that's a sort of an informal but pretty reliable way of visualizing the GAM fit, the nonlinear fit, and deciding whether you actually needed it in the first place. Well, we had other reasons above to think that we needed the GAM fit. It did better than the GLM in terms of other metrics. But here this tells you about the relationship between the response and the predictor value. It's nonlinear, and there are good reasons to think that it isn't linear in truth. And just to notice, it might be a little bit confusing that the label on this axis is this S of x1, and really the units on the y-axis are the log of lambda. And so, that's how you could interpret these units. You could exponentiate if you wanted to know the relationship between, lambda itself. All right, so going back up just a little bit, I wanted to mention one thing about this EDF that I write about down here. So the EDF shows up in the summary of our fit for x1. And EDF stands for estimated degrees of freedom. And we won't go into the math behind this, but basically EDFs that are close to 1 would suggest that maybe a nonlinear fit is not necessary. And then as the EDFs get larger, it suggests that the nonlinear relationship is necessary. So here we have a pretty large EDF, and that in conjunction with the plot that we just analyzed suggests that the nonlinear fit is necessary. And just as a comparison, in a previous video, we were looking at ozone data, and I showed you a plot of the fit of this IBT variable. And in that plot, we said, well, we probably could fit a straight line through the confidence bands. So we were being a bit informal there because we didn't know some of the details about the fit, the GAM fit. But we said, well, we could probably fit a straight line through those confidence bands. And so, maybe we didn't need the nonlinear fit from the GAM. And in that case, the EDF of IBT was about 2. And so that's closer to 1, suggests that a linear fit is okay. Here we have a larger EDF suggesting that the nonlinear fit is necessary. The last thing we'll take a look at here will be predictions. So let's imagine that we have some new values of the response that weren't in the data that we used to train the model. And let's try to use them to make predictions and see which model does best, right? The original GLM, the GLM where we knew the exact relationship, or the GAM. So here I've just constructed some new values of the predictors. I've calculated the true mu. Of course, I can do that because we know the true relationship. If we didn't, we would, we would not have that luxury. But here we can measure this against the ground truth. So this is just the response on the linear predictor scale, or actually it's not linear, on the predictor scale. So I'm just taking the log of the true mean. And then I'm computing the predicted values. So how does each model predict based on these new values that we've taken in? So again, we've trained the model on one data set. Now we're using those models to predict on a new data set, right, where we don't know the y's, but we have the x's. And so one measure that we can use is the predicted MSE. So I calculate 3 of them here. And if we notice down below, we get the 3 predicted MSEs. And for the original GLM, we have about 0.003. And then for the exact GLM, 0.0001. And for the GAM, 0.0003. So this is about what we should expect, right? The GAM does really well, not quite as well as the GLM where we know the true relationship, which we wouldn't know, but certainly better than the GAM that assumes a linear relationship. So that means if you were charged to use one of these models for predicting new data, you should use the GAM because you wouldn't have the exact fit GLM. All right, so hopefully that's enough to help you with question number 4 in this unit code, and hopefully it's enough for you to understand enough about using GAMs in R to ace the questions on the exam and to use them in the future if you need them.